This video is to go over multiplying and dividing radical expressions. So we're going to start with a few things, just a few rules. So these are things that you would definitely want to copy down, make sure they're in your notebook, and also, sometimes more importantly, make sure you write them out in your own words, that you actually understand what you're trying to say when you get notes in your notebook, because I feel like a lot of people write things down because the teacher wrote it, it was on the board, it's in the book, or you think you're supposed to write it, but you really have no idea what it means, okay? So this first rule right here is the M root. So M is representing a certain index of something A. A can represent anything, all right? Tons of different things. They must be real numbers, but it could be any real number, and your answer will be a real number rather. So the M root of B as well. That means if this is a cube root, then that's also a cube root. If that's a square root, then that's also a square root. When you have like indexes, all right, they're both the same index, and you're multiplying, it doesn't matter if you're radicand, the thing underneath your radical sign, it doesn't matter if they don't match, but you are allowed to multiply. When people see this on the board, they're like, okay, so you can't actually multiply them, you just put them next to each other? No, no. That means you multiply them. That's what that says to do, A times B. But do you have some secret thing that you know A times B is equal to C? I mean, when you write what the product of A and B is in using variables and constants and generals, that's how we write it. So if that were 2 and that were 3, that would be 2 times 3, or that would be a 6. There's just no other way to write it, okay? Here we have the continuation a little bit. Here we have an M root and we have an N root. So now we don't have the same root here. Okay, we don't have the same index. So this is a square root and a cube root. M and N are not equivalent to each other, so it cannot be multiplied any further. So this is just a little note, cannot be multiplied any further. That's all you're going to be able to do at this point in time. Okay. Here, another notation that we're going to have, M root of A to some power V. Okay, M is the index and V is the power that our radicand is being raised to. This is in radical form and this is in exponential form. These are things you definitely need to have written down, and again, you want to write them in your own words, okay? Make sure you know what this means. Well, V over M, V on top, M on bottom, means you're doing V divided by M. So if your V was something like 6 and your M was were 3, well, what's 6 over 3? You would actually write 2. You don't necessarily leave it at 6 over 3, okay? You'll actually get 2. When simplifying a radical, divide like a fourth grader. Example, 23 divided by 4 equals 5, remainder 3. So we're going to deal with this in a little bit here. So when we're taking a certain root, okay, you're taking a certain root, you might not be able to take everything out. You might not be able to take the root of the entire number, but or variable expression, but you might be able to take the root of some of it. That's why we're going to divide like a fourth grader. All right. Now here, just sort of another breakdown of this rule. If we have the N root of B to the W power, and B to the W power, I don't know how big this W is. If W is 10, then you're going to have 10 B's multiplying by each other inside of here, okay? And I don't know what N is. Is N less than W? Is N greater than W? Not sure. So we go on with this little bit of a rule here. If we could end up breaking down our B to the W, if N is less, if this B, the last one, when we multiply them all out, is less than N, all right? What else should I write over here actually? I would say here W is greater than N. So for example, if this were a 10 and this were a 3, well, this is bigger than this, right? So I would really have 10 B's, B times B times B, and then 7 more. Can I write that as B to the N times B to the N? If that were a 3, can I write it as B to the third? Sure. I could do a B to the third, a B to the third, and actually could do one more B to the third in there. And then what would I have left? I'd have a B to the 1, because 3 and 3 and 3 makes 9. And that's the 10th one, B to the 1. Well, the ones that you can take out, B to the N, what's the nth root of B to the N? It's just B. And what's the nth root of that B to the N? It's also just B. And the example I had made up with the 10 and the 3 would actually require one more out here. And then you're left with whatever's inside. Okay, so this rule seems a little nutty. okay? That'll become a b squared or b to the third, whatever it might be. But I'll elaborate on it when we get to an example, and you might want to come back to this part of the video and kind of rephrase this into your own words. So this and this sort of tie together, okay? This is an area where a lot of people do struggle. So here we got some examples. Can you simplify the product of the radical expressions below? Explain. Now, I'm not necessarily going to explain on the paper, but I will explain out loud. So here we have a cube root of 6, and here I have a square root of 2. So this is really the second bullet, okay? I have that m and n are not equal. My index and my index, they're not the same. Nothing there is an invisible 2, so we cannot multiply further, okay? Cannot be multiplied any further. That's it. Now, are there other things that sometimes you'll be able to do later in math when you're dealing with things in exponential form instead? Yes, there are going to be times where we can maybe do a little bit more. But for right now, we're done. We're going to leave it right there. Here I have a cube root and a cube root. So this sort of looks like my first bullet up there on the top of the page before, right? I have the same index. It doesn't matter if the numbers inside match or not, but we're going to be able to multiply them. So can I multiply these? Yeah, definitely. Negative 4 times 2 is negative 8. So this turns into the cube root of 8. Or actually, I'm sorry, negative 8. And what is the cube root of negative 8? What number times itself 3 times gives you negative 8? The answer is negative 2. Now, other ways that we can end up looking at this, you might want to know, when you have the odd root of negative 1, your answer is always going to be negative 1, okay? So that negative is definitely going to come out anyway. And then the 8, what is the prime factorization of 8? 8 is really 2 times 2 times 2. So when you go to take a cube root and you have that trio right there, well, the answer is 2 right there. So the negative comes out front, negative 1. So you end up with a negative 2 as your answer. This is just to elaborate, but this is a rule right here. When you have an odd root and there's a negative inside, okay? An odd root of negative 1, the answer is negative 1. Sort of similar to the square root of negative 1, all right, a couple chapters ago. That was equal to I, the imaginary unit I. Up here, I also make a reference to prime factorization in your little heart, okay? Because prime factorization, if you understand what numbers are really in like an x-ray scan of the numbers inside these radicals, these radicands in here, you're going to be much better off trying to simplify them. You're going to make a lot more progress. You're going to move a lot quicker, so that'll be really nice. All right, this one cannot be simplified. It's just like the first one. I know the numbers match inside this time, but that doesn't change the fact that the index of the first one is not equivalent to the index of the second one, so cannot be simplified further. All right, here I have 2 fifth roots, so I can actually find this product. What's negative 5 times negative 2? It's negative 10. And can you really go any further with this? Oh, not negative 10, I'm sorry, positive 10. Can I go any further with this? No, that's all we can do. 5 and 2 is already the prime factorization of 10, and there's no thing that I can write out 5 times or something to a 5th power or greater than a 5th power, so there's nothing we can do. We're really just done up to there, okay? So here that answer was negative 2, and here's just stay as it is, the 5th root of 10. Okay, we're going to do a little compare and contrast now. Square root of 24 versus the cube root of 24. When we're doing a square root, we're looking for something to a second power, or something to an even power, or something to a power bigger than 2, really. So I can help break this down a little bit more. And then here I have to go to a power 3 or more. Now, what's the prime factorization of 24? Don't be too over the top and sit there and make a factor tree like little kid style every single time, right? 24 is 6 times 4, wherever you chose to begin. 6 is 3 times 2, and 4 is 2 times 2. Sure, you're going to get the right answer, but this is kind of extra. You don't really need to do so much. So when I do these, maybe you already know the biggest perfect square in 24 is 4. The perfect biggest cube in 24 is 8. But are you going to know the biggest perfect square, the biggest perfect cube in every number? Probably not. Not off the top of your head anyway. So 24 is even, so I know it's 2 times something. 2 times what? 12. So whatever's left is going to be 12. And what's 12? 2 times 6. So this is 6. But what's 6? 2 times 3. And 3 is prime. Now that first step is really the same. You don't really have to write it, but I'm going to for right now. It's similar to the first step right here. Now, I always make up my little stories for how to solve these problems. So I kind of think there's an invisible 2 in here. And the 2 is sort of like this little troll that lives under the bridge, and he's just really annoying and makes his own rules for when you're going to pass him. So if you want to go, this is big old Radical is your castle, and if you want to go play outside, all these little royal children want to go play outside, the troll is going to be real annoying. You can only go outside and play in groups of 2. So this can go out and play, but this troll has the rule 3. You can only go out and play in groups of 3. Not if you're the number 3, but if you're in groups of 3. Well, what is this 2 times 2? This 2 times 2 is actually 4, and what is the square root of 4? 2. So really it's like this whole little package deal. That comes out as a 2 in front, and then I'm left with the square root of 2 times 3, which is 6. So there's my answer right there. Now how is this one different? This troll says you can only go out in a whole big group of 3. But that 2 times 2 times 2, like we said before, that's 8. And what's the cube root of 8? That's 2. So when the whole package comes out, it comes out as its root. So 2, cube root of, please make sure you put it really into that index, all right, so that it doesn't float out. It doesn't look like a 2 to the 3rd or a 2 times 3 or a 23. Some of you, your index gets mighty large, all right. So this right there is 2 cube root 3. It also means 2 times the cube root of 3. You don't need to put this dot right there, you know, to imply multiplication, but that's the operation that exists between them. This next set of examples asks us to find what is the simplest form of the given radical expression, product, or quotient. So you might just have an expression like we do right here, and another expression. Here we have a product, and in a second we're going to see some quotients as well, and we want to find the simplest form. So over here I'm asked to find the cube root of 54 x to the 5th. So again, the better you are at this, the faster you could sort of just jump to an answer. Obviously, I've been doing a lot of math for a very long time, and I can get to the answer pretty quickly. So when I break it down like this for you, I just have you know, this doesn't mean, you know, you always have to do it like this, and this is my idea of being good at it. No, being good at it is being able to understand this in your head, sure, or do it on paper, whatever works for you. Being good at it means getting the right answer, okay? And also not taking 10 years to do it or cheating. So 54, prime factorization, it's an even number, so it's definitely 2 times something. 2 times what? Well, what's half of 54? You could say half of 50 is 25. Half of 4 is 2. 25 and 2 is 27. So this is 27. You should know by heart, though, that 3 times 3 times 3 is 27. So 27 times 2 is 54. Now, x to the 5th, for this example, I'm going to be really ridiculous, and I'm just going to really write it out as 5 x's. I like to close my radical so I know I'm done. I'm all the way at the end there. I'm going to put the little multiplication dots, knock yourself out. So we have this cube root, and that's my little troll, and I can only go out of the castle in groups of 3. So here I have a group of 3, and here I have a group of 3, but I can't make another group of 3. I know 2x and x is 3 things, but it's not 3 of the same thing. This is really 3 to the 3rd power, and what is the cube root of 3 to the 3rd power? 3. This is really x to the 3rd power, and that's an x to the 2nd. But what's the cube root of x to the 3rd power? Just x. Here I'm left with the cube root of 2x squared. Now something else that sort of comes into play here and that we're going to have to remember is x is a variable, while 2 and 3, those are constants. 3 is positive, 3, and that's what it is, okay? It's a given set value. Where x is a variable and it can vary and change, constants stay the same. Well, x can be anything. So if x can be anything, is that safe to say? Because I'm going to take the cube root. Can I take the cube root and get a positive answer? Sure. Can I take a cube root and get a negative answer? Can I take a cube root and get 0? Yeah, sure. Anything really goes. So with odd roots, we don't have to worry about my variables so much. So really, this is your final answer. We can't simplify any further, but we'll see in a little while. We're going to see other cases, if you remember what I'm talking about already. Another thing I've asked you to practice many times is to make sure you know your 2 to a powers really, really well. So I'm just going to go down here and make a quick little list. 2 to the 0 power. Well, anything to the 0 is 1 except 0 to the 0. 2 to the 1st is 2. 2 to the 2nd is 4. 2 to the 3rd, 8. 2 to the 4th, 16. 2 to the 5th, 32. Now, obviously I'm going in order. This makes this much, much easier. These are things that you should really know really, really well, okay? 2 to the 6th, without even thinking about the 32, you should know that that's 64. All right, I've asked you to practice that. Can't force you, but definitely a good idea, okay? 2 to the 7th, is equal to 128. So can you see why I'm bringing this up? It's a good idea to know what the X-ray machine would see if you were really looking and investigating this 128. 2 to the 8th power is equal to 256. 2 to the 9th power is equal to 512. 2 to the 10th power is 1024. All right, you really want to make sure you're good at these, okay? Got to know them really well. Do you have to blurt it out immediately every time? No, but you really have to be comfortable with these and familiar with these. They do come up quite a bit. Let's write a few others down. 3 to the 3rd we mentioned before. That's 27. 3 to the 4th is 81. Okay? 3 to the 5th. Oh, it's not 3. 3 to the 5th is, sorry, it's such an ugly 3. 243. Definitely not a bad idea to know these really, really well, okay? Boy. I feel like it's like a 2 wearing disguise, like a mustache or something. Okay. So over here, 128, well, that's 2 to the 7th power. So you can kind of look at it in a couple of different ways. It's a lot of things in math and in life. It's all about perspective. So could I look at this as 7 2's being multiplied? 1, 2, 3, 4, 5, 6, and 7. Sure, you really could. I think this is silly, and I probably wouldn't do this normally. It's 4, 5, oh boy, 6, 7. Sorry, I have to open a door for my dog. So I'm going to be taking a cube root here. I'm just going to kind of underline my groups of 3. So there's 3 right there. That's a 2 to the 3rd and 2 to the 3rd. Cube root of 8 is 2. Cube root of 8 is 2. This guy, no buddies to go out with, so he's got to stay inside the castle. X, 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 no buddies, got to stay inside the castle. Alright, so what does that say about the answer here? This 2 comes out, and that 2 comes out, because it's both the cube root of the 8 there. And 2 times 2 is 4, so 4 is out there. Here again, x to the 3rd, cube root of that is x. X to the 3rd, cube root of that is x, so 4x squared. And inside we're left with a 2x. And really put that 3 in there so we don't mix up where it's supposed to be, and we're good. So that's one way of looking at it, again with the perspective. Now how else could I look at this? Well, we said 128 is really 2 to the 7th power. I'm going to divide like a 4th grader like we mentioned before. What is 7 divided by 3? How many times does 3 go into 7? It goes in twice, with a remainder of 1. So 1 remains inside. Same here. Twice, it goes in twice, 7 divided by 3, with a remainder of 1. Now, if you're looking at it carefully, you should be able to tell 2 to the 2nd came out. Okay, we're dealing with our exponent, our power. 2 to the 2nd came out, which is 4. X to the 2nd also came out, but we can't really do anything with that, other than leave it alone. And 2 to the 1st and x to the 1st is just 2x. So really, it's the same answer, just a different way of looking at it. So I would probably think of it more like this. I think this is neater, this is way more compact, but from there I wouldn't write 2 to the 2nd outside, I would immediately write the 4. But again, this all comes with practice, okay? We have another example, and here something that drives me crazy is when people make things harder than they need to be. There's no reason for you to multiply 72 and 10 and make it 720. When the next thing you're going to do is break down 720, you already have a head start. Just keep using the head start, okay? So 720, instead 72 and 10. What multiplies to give us 72? It's 2 times 36, and 36 is 6 times 6. Now, I'm not going to break these 6's down any further because I'm always looking for pairs with square roots, and I already have a pair. Here's 2. Now, can I buddy that 2 up with something from here? Sure can, because that's 2 times 5. So here is the 72. Okay. Right there's the 10. Now, x to the 3rd and x, that's x to the 4th. And y to the 2nd and y to the 3rd is y to the 5th. So these are square roots. So I've got a pair right there, and a pair right there. And I'm definitely going to be able to take care of some of the x's and y's. What's the square root of 36? It's 6. And what's the square root of 4? It's 2. And 6 times 2 is 12. So what am I going to do here? I'm going to make this a 12. Sorry. That 12 came out of there. And in the square root, the 5 is definitely left behind. Okay. 4 divided by 2. Well, that's x squared. 5 divided by 2 is 2, remainder 1. So right here is my final answer. I do have a square root, unlike the cube roots I had in the last two examples. The variables, which are the wild cards over here, could be anything. They're both being raised to even powers, which guarantees that these are going to be positive outputs, no matter what I have filled in for x and for y. So there's no issue with me worried about my square root and winding up being equal to some negative number, okay? It's definitely going to be a positive number, so I'm in the clear. Again, do you know what 45 times 35 is? Probably not off the top of your head. This is going to be 1575. If you know a little trick here, if you know the midpoint of these two numbers, which I know is 40, then I know it's going to be equal to 40 squared minus 5 squared. 40 squared is 1600, because 4 squared is 16, 10 squared is 100, so 1600. 5 squared is 25, and that's going to give me 1575. So yeah, sure, I know what it is, but I'm still going to need to break it down, so why would I do that if I could just start here? The reason this works is a squared minus b squared, in case you were wondering, maybe you don't care. That's the difference of two squares, and these are my conjugates. A plus b and a minus b. And 40 squared minus 5 squared. Well, if I factor that, I'll get 40 plus 5, 45, and 40 minus 5, 35. So the product of those two numbers is equal to their midpoint squared minus the distance they each are from their midpoint squared. So, I don't know, I'm a weirdo and I do things like this in my head all the time, but that's how I do that one quickly. So, square root of, what multiplies to give me 45? I need to make my prime factorization. 45 is 9 times 5, and 9 is 3 times 3. You could leave it a 9 if you're fine with that, but here's my 9 and my 5, and then 35 is 5 times 7. The x to the 5th and the x is x to the 6th, and the y to the 3rd and y to the 4th is y to the 7. Alright, so square root, what's the square root of 9? It's 3. What's the square root of 5? Oh, not 5, 25, it's 5. And then I can take care of some of this x and y material over here. So 9 and 25, I'm getting a 15 on the outside. 6 divided by 2 is x to the 3rd, odd power right there, y to the 7th. 7 divided by 2 is 3, remainder 1. So what's remaining inside is this 7 and a y, and I need absolute value bars on this x to the 3rd and this y to the 3rd, because if they end up being negative, negatives to an odd power are negative, and that would mean that somehow my answer to a square root was negative, and no bueno. So we put in absolute value bars, protect it, keep it safe, keep it positive. Okay? So that one is finished. Next example. Now, whenever possible, you do want to keep in mind that if you had the same radical on top and on bottom, on the numerator and denominator, you could really make it just one big radical and make it one big happy home. 18x to the 5th over 2x to the 3rd. Now, can you simplify your fraction within? Sure. This is going to be the square root of 9x to the 2nd, and the square root of 9 is 3, and the square root of x squared is x. Again, you don't want to forget your absolute value. 162 is actually 81 times 2, and 81 divided by 3 is 27, so I'm left with 27 times 2, which is 54. So we have the cube root of 54, and I'm also left with y to the 3rd power. We saw 54 earlier. It's actually up on top of this page right there, and it was also in a cube root. It was a 3 on the outside, and there was a 2 on the inside, because it's 27 times 2. And then y to the 3rd gives me just a y on the outside. I don't know why I made that radical so big, and that's the final answer, 3y cube root of 2. Now it's important to keep in mind that you're not allowed to have a radical in your denominator, so we may end up having to rationalize a denominator every now and then. Here I have 2 square roots, so I can make it one big square root. I will have a 25 when I deal with that, and I will have an x squared, and the square root of 25x squared is 5x with an absolute value. We have some examples here where we're going to need to rationalize the denominator. You might be used to examples where when you rationalize the denominator, it was a square root, so you multiplied by another of whatever was in the denominator or something along those lines. However, these are cube roots. Whatever the index is tells you how many of each factor you need in order to get rid of the radical. Okay, so what am I going to do? I'm going to sort of set this up by, I'm going to make it two separate ones just to kind of break things apart a little. You don't have to make it two separate ones, but that's how I'm going to start it off. 5x squared, those are already prime factors. I can see how many of each thing I have, so I know how many more I'll need to get a perfect cube. So I definitely have 2 squared, that's the 4, and I definitely have a 3. 4 times 3 is 12. I have y squared here, and I have z to the first. Now I want 3 of everything. That means I need to have another 2. Whatever I do on bottom, I have to do on top. Both going underneath this radical, okay? So I'm extending the radical to fit these numbers inside. Then I need 3 squared, because I need 3 of them. Right now I only have 1. 3 squared right there. I have 2 y's, so I need 1 more. And I need z squared. And z squared. Alright, now we clean this up. I now have 8 in there. What's the cube root of 8? It's 2. I also have a 27 in here. What's the cube root of 27? It's 3. 2 and 3 come out, so what is on bottom outside of that radical? A 6. I have y to the third, cube root of that is just y, and I have z to the third, cube root of that is z. If you need to kind of look at that again, if you need to rewrite it differently, you might want to pause or rewind and kind of analyze this a little bit further. Here, however, I do not have 3 of anything. I have 9 times 5, which is 45, times 2 is 90. So I have the cubed root of 90, x to the second, y, z to the second. Now the numerator is in a radical and my denominator is not, but this is now rationalized. So mission accomplished. We're done. Here I have another example, so I'm just going to kind of scoot over here and put it down there since I kind of took up some of the space. Alright, I have 7x on top, I have 5y squared on bottom, sort of broken down the way I had fixed this one already. So I'm just going to rewrite it so I have the room. So I have 7 and I have x, and I'm going to have to throw some more stuff up there. And I also have the cube root of the 5y squared. Okay, what do I need to make this one? I have no cube root on bottom anymore. Well, I need 2 more 5s. So I have 3 altogether. So it's 5 squared and 5. But if I give that a 5 squared, I have to give the top a 5 squared. Oh, sorry. And I have y squared, so I just need another y, and I need another y. On bottom, I now have 5 to the third power. And what is the cube root of 5 to the third? It's 5. I also have y to the third, and the cube root of that is y. And in my numerator, I have the cube root of, this is 25 times 7, so it's 175. And I'll have an x and a y. Nothing else to clean up here. We are done and done. That's it. No radical in the denominator. So like I said, you might have to rewind and watch this again to clear up what's going on in this step. But really you just need whatever the index is, you need that many of each number, and then you can get rid of your radical essentially.